My name is James Tolson. Matthew Colvin and I make up Team Space Coast Unmanned, and this presentation is our entrance into the Airspew Challenge. There are 4 objectives for this challenge. The first was to design a system that attaches to a DJI Phantom 4 without permanently modifying the unit, and to only use built-in DJI functionality for activation of the system. The second objective was to play audio output via a loudspeaker system. The third objective was the ability to incorporate a software-defined radio. This would allow radio transmission in the FM frequency and be compatible with GNU radio scripts. The fourth objective was the ability to carry 1 pound of leaflets and drop them during flight. Space Coast Unmanned solution allows all 3 modules to be mounted simultaneously to the DJI Phantom 4. This allows only 1 DJI Phantom to be operated at a time, giving cost savings to the end user for reduced fleet size and maintenance. The modules were designed not to interfere with the Phantom 4's built-in sensors. If there's a preference to separate the modules, the audio system could be redesigned for a higher volume output. On the right-hand side of the Phantom 4, you can see the leaflet dropper. It's operated by a single servo and a door on the bottom of the unit. The speaker system has been designed not to interfere with gimbal operation when mounted in this configuration. You can see that the gimbal is allowed full operation left and right. On the top right, you'll see the light sensor that is velcroed into the default LED location. On the left side of the Phantom 4, you can see the Raspberry Pi mounting module, as well as the FM transmitter and the audio amplifier. Disabled the audio amplifier, and this is a screenshot of my laptop running a software-defined radio. As you can see, we have Space Coast Unmanned in the top left of the radio identifier, an Airspew for the song. So we just activated the light and the music is playing. We'll start it off. And the music stops. And I'll show a shot of both at the same time. Here's a short clip showing the leaflet dropper dropping 1 pound of pamphlets. This is a demo video showing the flight capabilities of the Phantom 4 with our modules attached. As you can see, there's a small amount of wobble. This is induced by the antenna design. In the future, we'd use a carbon fiber boom instead of a plastic tube to increase the rigidity and reduce the wobbling. As you can see, the unit is still maneuverable and can be operated in a controlled manner in a tight space. There are multiple configurations. The leaflet dropper and the audio system can both be removed without any change to the code, or they can be added individually. Our design approach was to implement mature open source technologies where possible to minimize risk. We would also design and produce as many components as possible to reduce dependencies on outside resources or vendors, which reduces risk for future change and reduces procurement costs. This also allows greater customizability, and we can tailor the system to meet the customer's needs. We used 3D scanners to get an accurate model of the Phantom 4. All of our physical design was done in 3D CAD, which allowed us to optimize the design location for each module and avoid any interference with the Phantom 4 sensors. The custom components used in our system were all designed and manufactured in-house, which saves time and costs. It also allows us to transfer design files to manufacturing houses for large volume production. Per the competition requirements, none of our modules require permanent modification of the DJI. All the modules attached to the Phantom 4 using Velcro, which makes it quick and easy to assemble and disassemble the unit. To install the light module, you simply pry out the clear lens cap that covers the front LED, insert the light sensor, and attach it to the arm via Velcro. For the audio amplifier, we chose an off-the-shelf unit from Adafruit. This reduced development time and risk due to the fact that example code was provided with schematics. The board uses a Texas Instruments chip, and in future versions we could purchase the Texas Instruments chip without the Adafruit unit to reduce the cost. The amplifier is a Class D amplifier, which is around 90% efficient. This allows longer battery life while maintaining high output volumes. For the computing node, we chose Raspberry Pi for multiple reasons. It has plenty of processing power. It runs on a Linux OS, which would allow GNU radio compatibility. It has a small form factor and a low cost. There's also a large pool of resources available online, so that development and future modifications can be done easily. We successfully designed, built, and tested a high-efficiency power supply. This uses a switching regulator, which is roughly 85% efficient at 9 volts or 80% efficient at 12 volts. The FM transmitter was another breakout unit from Adafruit. This allowed us to get example code and schematics to quickly get a transmitter working. In the future, we can simply purchase the Silicon Labs chip without having to buy the entire breakout board, which would save cost. The SI4713 does not have enough output power to meet the Airspew Challenge design requirements, so an external RF amplifier was designed. The RF amplifier uses 2 stages of amplification. These were designed in SPICE simulation, and the schematics are available at Space Coast Unmanned's GitHub repository. Accounting for losses, the theoretical output is between 14 dBm and 41 dBm, although the unit is only rated for 24 dBm without distortion, and sustained outputs over 28 dBm may lead to damaging the amplifier. The first stage of the amplifier uses a BGA 2867 small signal amplifier with internal matching. This screen capture shows the SPICE circuit and SPICE simulation output. The yellow rectangle shows the power in versus power out ratio, which is a roughly 6 dB loss. This is accounted for and one of the reasons why we used multiple stages of amplification. The second stage of the RF amplifier uses a larger chip that is rated at 24 dBm output without distortion. With the current design, we don't recommend operating the system at over 26 dBm output, which is 400 milliwatts. The screen capture shows the SPICE circuit and simulation output for the second stage of the RF amplifier. The red rectangle represents the input stage of the amplifier. The components before this are a low-pass filter designed to minimize any interference on higher frequencies than the FM band. The yellow rectangle shows the power input versus power output ratio. Once again, it's roughly 6 dBm of loss, so this was accounted for in the design. We manufactured several RF amplifier boards using our in-house CNC. Unfortunately, due to the small tolerances, we were unable to produce a unit that worked completely. Because we designed the RF amplifier in-house, we can easily transfer our schematics and bill of materials to a manufacturer to have these mass-produced. The pamphlet dropper has been tested to hold 1 pound of leaflets. There's a single servo that controls it, and it releases all pamphlets at once in accordance with the clarification provided during the Q&A session. Because we designed and manufactured this in-house, if there is a desire to drop 1 leaflet at a time, we could easily modify the design to meet this. In the future, all of our designs can be transferred to manufacturers, which would allow bulk buy pricing and also reduce any components that are not necessary for the system to operate. This results in a lightweight and efficient system with the lowest cost possible. In summary, Space Coast Unmanned solution offers a system that attaches to a DJI Phantom 4 without any permanent modifications. All features are activated using built-in DJI functionality. The audio is played via a loudspeaker system. The Raspberry Pi can easily incorporate a software-defined radio, and it currently transmits in the FM frequency. The leaflet dropper can hold up to 1 pound of pamphlets and drop them simultaneously. For future improvements, Space Coast Unmanned would do further development to lower the weight of the modules using composite materials. The audio volume could also be increased by developing a larger speaker module, although this would mean that the speakers cannot be run in conjunction with the leaflet dropper. We would also like to discuss the possibility of using a purpose-built UAV platform instead of the DJI Phantom 4. This would allow a larger version of each module, which could result in longer battery life, more pamphlets, and a louder speaker. A PDF of this presentation can be found online, along with our circuit schematics and all of our designs at our GitHub repository, shown in the link below.